All right, I promised that we would look quantitatively at Le Chatelier's principle, and let's do it. And some of you may like this better than the qualitative option. So what I'm going to start with is the reaction of N2O4 in equilibrium with 2NO2. I'm going to start with actually absolutely everything from the problem that we ended with, which was that I had point 1 and 1, I got to equilibrium, I got my equilibrium concentrations of 0.4083 and 0.3834. And I know that my equilibrium constant is 0.36 at 100 degrees. So this is exactly where I'm starting. I have equilibrium concentrations, I have a reaction, I have an equilibrium constant. The the problem that I'm going to solve here is that this reaction at equilibrium, I'm going to add zero point 0.2 molar of N2O4. So qualitatively, I could say I'm increasing a reactant. My reaction is going to move to the right, and that's it. That's all you can say qualitatively. I would like you to find the new concentrations at equilibrium after this perturbation. So I'm going to just expand my rice table here because the reaction lets me organize everything. So I'm adding 0.2 molar of N2O4. So I've got it in red, like I'm making an add row, which doesn't really fit in rice, but it's organized. So I'm going to add zero point 0.2 just to the N2O4. This means that my flask now has 0.6083 N2O4 and 0.3834 NO2. These are my new initial conditions. So now from this point, my reaction is going to move. Now I know from my qualitative thoughts that it's going to move to the right, but we don't even need to rely on that to get to equilibrium. So I could say this is my initial row. I mean, it's the new initial conditions, but they're initial from where I have decided to start looking at this. It's going to change in some way to get back to equilibrium. Let's just fill in the rest of the rice table. So if the conditions are 0.6083 molar and 0.3834 molar, what you should find is that Q is less than K. So try this if you need to convince yourself. Calculate Q, compare it to 0.36, and Q will be less than K, which means your reaction has to move to the right. So you will lose whatever amount of N2O4 you lose, and you will gain whatever amount of NO2 you gain. So minus X under the N2O4 and a plus 2X under the NO2. At equilibrium, this means that my N2O4 has a concentration of 0.6083 minus X, and my NO2 has a concentration of 0.3834 plus 2X. Products over reactants in the equilibrium constant expression means that on top I have 0.3834 plus 2x whole quantity squared divided by 0.6083 minus x, and this is all equal to 0.36. So right now we have to algebra. You have to multiply through, distribute, all of those algebra things. And what you should get in the first pass is 0.218988 minus 0.36x. So that's my denominator cross multiplied with the 0.36 equal to 0.146996 plus 1.5336x plus 4x squared, which you can rearrange to set it all equal to 0 and then do quadratic formula. When you do quadratic formula, you will get negative 0.50878 and 0.035375. I mean, thankfully the rejection part was kind of stand out. We have a negative value here. We can reject that one. It would give us a negative concentration. and 0.035375 is the correct value of X for our reaction, which means that at this newly established equilibrium, my N2O4 concentration is 0.5729 molar, my NO2 concentration is 0.4542 molar, and that's my final answer because I was asked to find the concentrations at the new equilibrium. But you can also check your answer, right? You could take these concentrations and plug them into the expression and see if you get the equilibrium constant.